We're now going to start a new section on magnetism, and this section covers about 20% of the AP exam, and usually one of the 3 free response questions deals with magnetism. So for the past 3 sessions, we've been covering electric fields, which, as you know, are generated by electric charges. Magnetic fields, on the other hand, are generated by either magnets or moving charged particles, such as the current. Just as we could draw electric field lines, we can also draw magnetic field lines. However, for magnets, there's one thing to note. Magnets always exist in dipole form. You will never see a monopole magnet. So, what do I mean by monopole? Here is an example of a monopole electric source, specifically a positively charged ion, in which you have electric field lines going away from this positive source. However, over here with magnets, you see that the magnetic field lines will leave one end of the magnet, and they will always bend around and come back towards the other end. So in magnets, you will always have both a source and a sink. You will never see magnetic field lines go away from a particular source or magnet and never come back. Right? They will always bend around, such that magnets are always in dipole form and never monopole form. But now I want to focus on how magnetic forces affect moving charged particles. And the equation that governs this relationship is specifically that the force exerted by the magnetic exerted by the magnetic field is equal to the charge of the moving particle times the cross product of the velocity vector of the moving particle and the magnetic field vector. And before I forget, so just as we use E to represent an electric field, we use B to represent a magnetic field. So looking at this equation, we can see a couple of things. First, the particle has to be charged in order to experience a magnetic force. Second of all, the particle has to be moving in order to experience a magnetic force. If the particle is stationary, say sitting right here, and not moving, it will not feel the effect of the magnetic field. We also see that there's a cross product in the equation, which is pretty interesting. Do you remember how cross products are evaluated? So the magnitude of a cross product is equal to the magnitude, is equal to the product of the magnitude of the individual vectors multiplied by the sign of the angle between the 2 vectors. Alright, so say this is our xy coordinate, so say this blackboard plane here is in xy plane, and say we have a positively charged ion moving in this direction, so this is its velocity vector, and say that the magnetic field at this point is pointing sort of upwardish, like that. Right? So the angle that we're interested in when we want to calculate the magnitude is which one? Yeah, it's this one. Let's call it C. So the magnitude of the magnetic force vector is equal to Q V B sine B. Great. So this is the magnitude. What about the direction? So to evaluate direction, we use something called the right-hand rule. And it's called the right-hand rule because you use your right hand. So I want all of you to take your right hand and point your fingers towards the direction that the particle is moving in. So in this case, we're going to orient it this way. Right? And then the next thing you do is you curl your hand towards the direction that the magnetic field is pointing. So we see that in order to do that, we have to sort of flip our hand around and then curl it this way. You see that? So initially it was in the V direction. Now curl it towards the V direction. And we see our thumb is pointing this way. Indeed, it's actually pointing out of the board. And so the direction that your thumb points in is the direction that the magnetic force acts in. So the magnetic force is actually pushing this particle this way out of the board. And so if we let this be the Z direction, the force is pushing the particle in a positive Z direction. So as you can see with cross products, we have to deal with a three-dimensional environment, which can make things rather tricky because, you know, we're working on a two-dimensional piece of paper. So is there a way to sort of help us simplify, I guess, notations with three dimensions? And the answer is yes. Right? So there is one convention that you can use that everyone else will understand, and that is, so if I have a field that's coming out of the plane, sort of, in this case, in the positive Z direction, I can simply draw a series of dots. And people will understand that. I'll label this B. People go, oh, okay, I know. A field is coming out of the plane in the positive Z direction at this location here. Similarly, or not similarly, if I draw a series of X's here, and I label it B, when you see this, right, you should know that this means that a magnetic field is going into the board in a negative Z direction in this location. So how do you remember this? So what I do is I think of magnetic fields as arrows. Right? So with arrows, you have a pointy head and a feathery tail, if you will. So when the arrow is coming at you, you're going to see its pointy head, sort of like a dot. So you can think of it as, so when you see an arrow coming towards you, coming out of the board, you're going to see dots. So hence, when you see dots on a piece of paper, you know that this field is coming out of the board towards you. Similarly, when you see X's, you can think of it as, oh, X's, the tail end of the arrow. That means that the arrow is going into the board, away from me, in a negative Z direction. So that means that this field is going into the board. Right, so hopefully this arrow image will help you remember which one to switch. Anyway, so now we just talked about the right-hand rule and also this new notation. So why don't we use it in some examples? So example 1. Right? Let's say I have, so what does this represent? This represents a B field going in or out of the board. Out, right? Oh, before I forget, let me just label this. So this means out of plane. And plane, I mean this XY coordinate plane. And this means into plane. And before I forget, does anyone have any questions regarding this? Right? Feel free to interrupt me whenever. Right? So I'll go with this. Great. Alright, so this means coming out of the plane. And say I have a positively charged ion and it's moving in this direction. So it's moving in this direction. So my question is, what's the force? What direction is the force? It's a magnetic force acting on this particle. So what you do is take your right hand, point it this way. The B field is coming out, so you have to curl your hands like this. Can you guys see that? So I put